Hello everyone and welcome to this video on permutation and combination. In this video we'll understand the concepts of permutation and combination. But before that we'll understand some basic rules which are essential for understanding the concepts of permutation and combination. Then we will derive the formula for permutation and combination and see how to modify these formulas for conditional selection, conditional arrangement, conditional distribution and group formation. And then finally we will understand the concept of circular permutation and dearrangement. So let us begin. M by N rule. This is the most basic and the fundamental rule that you need to understand in order to solve problems based on permutation and combination. So what does this rule states? Suppose there are two tasks A and B. There are m ways for performing the task A and there are n ways for performing the task B. So the total number of ways in which the task A and B can be completed will be given by m into n. This rule can be extended to any number of tasks. Suppose there was one more task C which can be performed in P ways. Then the total number of ways in which A, B and C can be performed will be given by m into n into P. Let us understand this with the help of an example. Suppose there were three cities, say A, B and C. Now the number of routes for going from city A to city B are, let's say, 4. There are 4 routes: A1, A2, A3 and A4. Now from city B to city C there are another 3 routes, say B1, B2 and B3. So in how many ways can you go from city A to city C? So either you can take this route A1 B1 and you can reach from A to C, or you can take the route A1 B2, or you can take the route A1 B3. In the similar way, for going A to B you can take the route A2, and for going B to C you can again take any of these 3 routes. So for going A to B there are 4 routes, and for going B to C there are another 3 routes. So the total number of ways in which you can go from A to C will be given by 4 into 3, which will be 12 ways. You can count those ways manually. So for A1 there were 3 routes, for A2 there will be another 3 routes, likewise for A3 and A4 there will be 3 more routes. So the total number of routes will be equal to 12. As I have said previously, you can extend these rules for any number of tasks. Had there been another city, say city D, and the number of routes for going from city C to city D had been, let's say, 2, then the total number of ways by which you can go from A to D will be given by 4 into 3 into 2, which will be equal to 24 ways. This is the most basic and fundamental rule which will help you in understanding the concepts of permutation and combination. Let us now see another rule, OR rule and AND rule. So in problems of permutation and combination, and even in probability, wherever you see the word OR, we'll replace that word by plus sign, and wherever you see the word AND, we'll replace that word by multiplication sign. Let's consider this example. Number of ways of selecting 2 vowels or 3 consonants from the word healing. So if you want to find the number of ways for doing this task, first we'll find the number of ways for selecting 2 vowels, and to that we'll add the number of ways for selecting 3 consonants. In this second example, the number of ways of selecting 2 vowels and 3 consonants from the word healing. So if you want to find this, we'll first find the number of ways for selecting 2 vowels, and then we'll multiply it by number of ways for selecting 3 consonants. So in this way you can complete this task. How to solve these two problems? We'll come back to it. Let us first understand the concepts of permutation and combination now. So what is permutation and what is combination? Combination basically is the number of ways of selecting things, or it is a selection technique, whereas permutation refers to the arrangement of items. So wherever you have to make only selection, you will use combination, and in cases where you need to select and arrange those things, you can use permutation. Let us understand the difference between permutation and combination with the help of an example. Suppose there are three chocolates, let's say C1, C2 and C3, and this is you and you have another friend. And now you have to select two chocolates. The first chocolate that you select, you will give it to your friend. And the second chocolate that you will select, you will eat yourself. So in how many ways can you select two chocolates out of these threes? This is your first and this is your second chocolate. So the first chocolate out of these three, let's say you selected the chocolate C1. So this chocolate you will give it to your friend. Now out of these three, C1 is gone. For your second selection, you will have only two options, C2 and C3. So out of these two, you can select anyone. So if you selected C2, you will eat C2. Likewise, you can also select C3 as your second option. So in this way, you can select two chocolates. There is another way in which you can select. Your first chocolate can be C2, your second chocolate can be C1, first chocolate can be C2, second can be C3. Similarly, your first chocolate can be C3, second can be C1 or C2. In this case, as you have noticed, the order in which you are going to select these chocolates is important. Let us consider this group of chocolates C1 and C2. So we have C1, C2 here and we have a C1, C2 here as well. So if you have selected C1 as your first chocolate, this will go to your friend. Had you selected C1 as your second chocolate, you will get to eat C1. So here the order in which you are going to select the chocolates is important. Based on your selection, either you will eat the chocolate or your friend will eat the chocolate. So as you can see, there is one pair of C1, C2. There is one pair of C1, C3 here and C1, C3 here. Then we have C2, C3 and C2, C3. So in all of these cases, the order in which you are selecting the chocolates will decide which chocolate your friend will get to eat and which chocolate you are going to eat. So in such cases where the order is important, we will use permutation. So the total number of ways in which you can select these chocolates will be 6 ways. Let us consider another case in which there are again 3 chocolates C1, C2 and C3. In this case, your friend is not there, only you are there. Again, you have to select 2 chocolates, and both these chocolates that you are going to select, you are going to eat them. You are not going to give this chocolate to your friend. So in this case, it does not matter in which order you select these chocolates. As in the previous case, it was important to consider the order as well, because had you selected C1 first, you will have to give it to your friend. Had you selected C1 second, you would get to eat that chocolate. But in this case, it does not matter whether you select C1 as your first chocolate or C1 as your second chocolate, because both the chocolates only you are going to eat it. So the number of ways in which you can select these chocolates will now be either you can select C1, C2, or you can select C1, C3, or you can select C2, C3. Now C1, C2, selection of C1, C2 will be same as selecting C2, C1, because the order does not matter here. And similarly, selecting C1, C3 will be same as selecting C3, C1. Whereas C2, C3 will be same as selecting C3, C2. So the order does not matter here. So in this case, we will use the concepts of combination. So the total number of ways in which you can select these chocolates in the second case is 3. In the first case, the number of ways was 6. In the second case, it is 3. So as you can see, in the first case, there were 2 people here, you and your friend. So if you multiply this value of combination with 2 factorial, you will get your answer as 6. This is the answer for permutation, where the order is important, and this is your answer for combination, where the order is not important. We'll understand from where this 2 factorial is coming in a little while. Let us first derive the formula for permutation. Now suppose in the box that we are considering there are n chocolates and you have r number of friends. And now you want to draw r number of chocolates for each of your friend. So in how many ways can you do this? So when you draw the first chocolate, you will have total n options available to choose from. So for your first chocolate, you will have n options. Then after that, you have taken out one chocolate. Now in this box, there will be n minus 1 chocolates left. So for selecting your second chocolate, you will have n minus 1 option. Now after that, you have taken two chocolates out from this box. Then in the box, there will be only n minus 2 chocolates. So for selecting your third chocolate, you will have n minus 2 options. In this same way, for selecting your rth chocolate, you will have n minus r plus 1 options. For your first chocolate, you had only n options. For your second chocolate, you had n minus 1 option. For your third chocolate, you had n minus 2 options. So for your rth chocolate, you will have n minus r plus 1 options. So in this way, you can select the chocolates for your friends. So this is your answer for permutation, where the order of your selection is important. Now we'll modify this formula a little bit. We'll multiply this numerator by the next term, which will be n minus r, because we want to convert it into n factorial. So it is n into n minus 1 into n minus 2. This is n minus r plus 1. So the next term will be 1 less than this. So this will be n minus r plus 1 minus 1. So plus 1 and minus 1 will cancel out. We'll get n minus r. Then the next term will be 1 less than this term. It will be n minus r minus 1. Then n minus r minus 2. And all the way up till 3 into 2 into 1. So this will now become equal to n factorial. Now since we have multiplied the numerator by these terms, which is n minus r into n minus r minus 1 into n minus r minus 2, we'll divide the denominator by the same term, so to balance it out. So in the denominator, we'll get n minus r into n minus r minus 1 into n minus r minus 2 and so on up till 3 into 2 into 1. So in the numerator, we'll be getting n factorial, and in the denominator, we'll be getting n minus r factorial. So this is your final formula for permutation, and this formula is denoted as NPR, where you have to arrange r items out of n items. Now let us see the formula for combination. In the first example that I have given you, the permutation came out to be 6 and the combination came out to be 3. So the permutation was 6 and combination was 3. From combination to get permutation, we had to multiply it with 2 factorial. Why? Because there were 2 friends. Let us take one more example. Suppose there were 5 chocolates, C1, C2, C3, C4 and C5. And let's say there were 3 peoples, P1, P2 and P3. And you have to distribute these 5 chocolates to these 3 people. So how you would do this? So first you will take first chocolate and then you will give it to person 1. Then you will pick up the second chocolate, give it to person 2. And then you will take the third chocolate and give it to the third person. Suppose you take these 3 chocolates first. In how many ways can you distribute these 3 chocolates to these 3 people? You can give the chocolate 1 to P1, 2 to P2 and chocolate 3 to the person 3. Or you can still give chocolate 1 to first person, but you can give C3 to the second person and C2 to the third person. Or you can change this order, C2, C1, C3, or you can make it as C2, C3, C1. Or you can give the third chocolate to the first person, first chocolate to the second, and second to the third. Likewise, you can get C3, C2, and C1. Now as you can see, since there are 3 people in which you have to distribute these 3 chocolates, you can do this distribution in 6 ways. This 6 ways is nothing but 3 factorial. In the previous case, there were only 2 people, you and your friend. So that distribution of 2 chocolates, C1 and C2, could have been done in 2 ways. That was your internal distribution. After choosing those chocolates, you are distributing. The manner in which you can distribute will be given by 3 factorial. So as many number of people are there, or as many number of selections that you need to do, that many ways in which you can internally distribute those things. So in combination, we do not need to take all the possible ways in which the distribution can be done. We just need to select one of the ways, because in combination, the order in which the things will be distributed is not of any importance to us. We just need to make sure that these particular things are selected. So the formula for combination will be given by the formula for permutation divided by r factorial, since we are selecting r things. So this will become NPR, as we have derived, it came out to be n factorial upon n minus r factorial into r factorial. So your formula for combination will be n factorial upon n minus r factorial into r factorial. So this formula is basically selection of r things out of n distinct things. And this formula for permutation is basically the arrangement of r things out of n distinct things. Now let us go back to the previous question that we have left. In this, we have to find the number of ways of selecting 2 vowels or 3 consonants from the word healing. So let us first count how many vowels are there. So E, A and I, there are total 3 vowels, and consonants, there are 1, 2, 3, 4. So now you need to select 2 vowels out of these 3. So we'll use combination, that will be given by 3C2, and you need to select 3 consonants out of the 4 consonants which are available. So this can be done in 4C 3 ways. Now since we have OR here, so we will add these values. Whereas in the second case, we still need to select 2 vowels and 3 consonants. So the formula will remain the same, C2 and 4C3. And since we have a AND over here, we'll multiply these 2 formulas. So this will become 3 factorial upon 3 minus 2, which will be 1 factorial, into 2 factorial. So the value of this will come out to be equal to 3. And from here we'll get 4 factorial upon 4 minus 3, which will be 1 factorial, into r factorial, which is 3 factorial. So this value will come out to be equal to 4. So for this question, we'll have to add these 2 values. So this will be 3 plus 4, which will be 7 ways. So there are total 7 ways in which you can select 2 vowels or 3 consonants from this word healing. Then the total number of ways for selecting 2 vowels and 3 consonants. So we'll have to multiply these values. So it will be 3 into 4, which will be 12 ways. So there are 12 ways in which you can select 2 vowels and 3 consonants from this word healing. Let us now see how to apply these formulas of permutation and combination under different situations. Now in this case, you have to select r things out from a group of n dissimilar things. So we need to select r things out of n things. So these are all dissimilar things, and from this we need to take out r things. So this can be done by using the formula NCR, the same formula that we have derived. So this is n factorial upon n minus r factorial into r factorial. So you need to make a selection of r things out of n dissimilar things. In the second case, you need to select any number of things from a group of n dissimilar things. In the first case, you had to select r things. So the value of r was fixed. Like in the previous examples of chocolate, you had to select 2 chocolates, one for your friend and one for yourself. But in this second case, you can select any number of chocolates. So the value of r will be from 0 to n. So if there were 5 chocolates, C1, C2, C3, C4 and C5, so in this you had a freedom. You can select either 0 chocolates, or you can select 1, 2, 3, 4 or 5. You can select any of these chocolates. Whereas in the previous case, the value of R was fixed. It could be either only 2 or only 4. Only a single value of R was there. But in this case, the value of R, you can take any of these values. So how this can be done? So for selecting zero number of things from a group of n dissimilar things, we'll use the formula for NC0. Then had you decided to select only one thing, so this can be done in NC1 ways, or you could have decided to select only two things, so this could be done in NC2 ways, or you could have decided to select three things, this could be done in NC3 ways, and so on so forth up till NCn ways. Because you had a freedom to select any number of things from 0 to n. Now this value of NC0 plus NC1 plus NC2 plus NC3 is equal to 2 raised to n. So we will directly use this formula in cases where we have to select any number of things from a group of n similar things. When we have to select r things from a group of n similar things, we'll use this formula for NCR. Let us see now the third case. In this we need to make a selection of r things from a group of n similar things. In the previous two cases that we have considered, the things were dissimilar. In this case, the things are of same type. So let's say now there are again 5 chocolates, and all these 5 chocolates are of same nature. So they are exactly same. So there are 5 chocolates. So now if I ask you to select one chocolate from this group, you can select any one of these chocolates. It does not matter. So there is one way of selecting one chocolate. Now what if I ask you to select 2 chocolates from this group? So in how many ways can you select 2 chocolates? You pick the first chocolate and the second chocolate, or you pick the third or the fourth. It does not matter because all of these chocolates are same. So there is only one way in which you can select these chocolates. It does not matter what is the value of R. Since all these chocolates are similar, there is only one way of selecting these chocolates. So if you had to select one fixed number of chocolates, that is, let's say R number of chocolates from a group of n similar things, there is only one way in which this selection can be done. Now let's take this fourth case in which we have to make a selection of any number of things from a group of n similar things. Now from these 5 chocolates, you have been given a freedom of selecting any number of chocolates. You can select 0 chocolates, you can select 1 chocolate, you can select 2, 3, 4 or all 5. For each of these selection, you have just one way. For not selecting any of this, there is one way. That is, you do not select any of them. For selecting only one chocolate, there is again only one way, since all these chocolates are same. For selecting 2 chocolates, again you pick up any of these 2, it will be the same. So there is one way. So likewise, for even 3, 4 and 5 chocolates, there is one way for selecting each of these chocolates. So if there are n chocolates in this box, there will be n plus 1 ways, because for selecting 0 chocolate we have to count one extra one, and for rest of all these n chocolates from 1 to n there will be n ways. For selecting 0 chocolate there will be one way. So the total number of ways in which you can select any number of things from a group of n similar things, it will be n plus 1 ways. So please understand the difference between the first two cases and the last two cases that we have taken. In the first two cases, we had to select from a group of dissimilar things. Whereas in the second case, we had to make the selection from similar things. Let us now see how to make selection from multiple groups. In this case, there are 3 groups, let's say A, B, and C. So this group A consists of X number of elements numbered from, let's say, X1, X2 and all the way up till XX. So there are X elements in this group. There is another group B which contains Y number of elements numbered as Y1, Y2 and all the way up till YY. There is a third group as well that contains Z number of total elements. and the elements in this group are numbered as Z1, Z2, Z3 all the way up till ZZ. Now from these three groups you need to make a selection of any number of things. So let's see how it is to be done. There will be two cases. In the first case, the elements in each of the individual groups are similar. So when the elements in each of these individual groups are similar, that is x1 is equal to x2 is equal to x3 and so on up till xx. Likewise for the second group and the third group, all the elements in each of the individual groups will be equal. So for selecting any number of elements from each of these three groups, what we will do is we'll first select element from the first group and we'll select element from the second group and we'll select the element from the third group. So the number of ways in which any number of elements can be selected from a group that contains similar things will be given by number of elements plus 1, as we have seen previously. This is for the first group A. For the second group, we can select any number of elements from the second group in y plus 1 ways. Likewise, from the third group, we can select any number of elements in z plus 1 ways. Now since we need to make a selection from all of these three groups, so from first group it is in x plus 1, second group it is in y plus 1 ways, and the third group it is in z plus 1 ways. So combined we can select it into x plus 1 into y plus 1 into z plus 1 ways. In the second case, the elements in each of the individual groups are dissimilar. So how can we select any number of elements from a group of dissimilar items? It can be done into 2 raised to the number of elements in the group. So from the first group, the number of elements are x. In the second group, the number of elements are y. In the third group, the number of elements are z. So the total number of ways in which any number of elements can be selected from a group of dissimilar items, it is 2 raised to x into 2 raised to y into 2 raised to z, which can be written as 2 raised to x plus y plus z. So in these many ways you can select any number of items from three groups. So in this way you can apply this formula for selection from groups. This formula is not restricted to only three groups. You can add as many number of groups as you want. Had there been, let's say, a fourth group containing a elements, so this formula will be extended to a plus 1. Likewise, even this formula can be extended to 2 raised to x plus y plus z plus a. So this is the basic idea of selection from multiple groups. Let us now understand the concept of conditional selection of things. So in this case, we need to make a selection of r things out of n distinct things such that there are few conditions that we need to take into account. The first condition is that k particular things are always included. So in how many ways can you make a selection of r things out of n distinct things? It can be done in NCR ways. Now in the first case, k particular things are always included. So out of the r things that you need to select, k things have already been selected. So now you need to select only r minus k things. Now initially there were total n things. Out of these, k things are gone. They have already been selected. So the total number of things left is n minus k. So now you need to select r minus k things out of n minus k available things, because k particular things have already been selected. So this can be done in n minus k c r minus k ways. In the second case, k particular things are always excluded. So now you need to make a selection of r things out of a group of n things, but from these n things there are k things that you can never select. So you'll have to subtract this k. So now only the ones which are available for selection will be n minus k. So this can be done in n minus k c r ways, because k particular things are always excluded. They can never be selected. In the third case, k particular things are never included together. So the total number of ways in which you can select r things out of n things is given by NCR. So from this we'll subtract the number of ways in which k particular things are always included. So this will give us the number of ways in which a selection can be made where k particular things are never included. So this is the total number of ways. From this we are subtracting the total number of ways in which k particular things are always included. This will leave us with the number of ways in which k particular things are never included together. Now let us understand one small concept. Number of ways of selecting k consecutive things out of n things in linear arrangement. Let's say there are 5 people A, B, C, D, E. Now out of these 5 people you need to select 3 people consecutively. So in how many ways can you do that? You can select ABC, that's one way. Then BCD, that's another group of 3 consecutive people. Then you can select CDE, that's your third group of 3 consecutive people. Now there is no more group that you can form of 3 consecutive people. So when there are n people of which you need to select k consecutive people, then this can be done in n minus k plus 1 ways. So in this case the total number of people were 5 and you needed to select 3 people consecutively. So this can be done in 5 minus 3 plus 1, which will be 3 ways. Which are those 3 ways? We have seen ABC, BCD or CDE. So this is all about combination. Now let us see how to apply the formula for permutation under different cases. So this is about conditional arrangement of things. Now if you want to arrange n people in n places, so there are, let's say 1, 2, 3, 4, 5 places, and at these 5 places you need to arrange 5 people. So for first place you have 5 options. You can select any of these 5 people. So one of these 5 person will come and sit here, let's say A. Now out of those 5 people, 1 is gone, so 4 is left. So for the second place you will have only 4 options. Likewise for the third place you will have 3 options. Second place you will have 2 options. And for the first place you will have only 1 option. So if you want to arrange 5 people in 5 places, it can be done in 5 into 4 into 3 into 2 into 1 ways, which is nothing but 5 factorial. So if you want to arrange n people in n places, it can be done in n factorial ways, which we can also arrive at using the formula for permutation, which is NPR is equal to n factorial upon n minus r factorial. So here the value of r will be equal to n, because we need to arrange n people in n places. So this will become npn will be equal to n factorial upon n minus n factorial, which will be 0 factorial. 0 factorial is nothing but equal to 1. So this will be equal to n factorial. So n things can be arranged in n places in n factorial ways. Now we'll consider different cases. In the first case, out of the total n people, x of them has to be seated always together. So let us take the first example that we have considered. There are 5 seats, and on these 5 seats we need to arrange 5 people. Let's say A, B, C, D and E. Now if we want A, B and C to always sit together, so how can we make this arrangement? So what we will do is we'll consider these 3 people as one single group. So this one group will occupy 3 places and the remaining 2 people will occupy the remaining 2 places. So how can I make the selection of the 3 places? I can make them sit on the first 3 places, or I can make them sit on the second, third and fourth place, or I can make them sit on the last 3 places. So in any case, whenever I choose a group of 3 places, I'll be left with an additional 2 places. So in other words, I'll have to make an arrangement of 3 people on 3 places. These 3 people will be this one group and these additional 2 people. So this can be done in 3 factorial ways. So had there been n people of which x have to be seated always together, so these x people will be considered as one group. So out of these n, I'll subtract these x people, and since they will be considered as only one group, so we'll add 1. So these n minus x plus 1 people can be seated in n minus x plus 1 places in n factorial ways. Now let us consider on the group of these three peoples. So for this group of three peoples A, B, C, they are always together. They are sitting side by side. But in which order are they sitting? Are they sitting like this way, ABC, or are they sitting as ACB, or BAC, or BCA, or we have another two combination CAB or CBA. So in which combination or in which arrangement are they sitting? If this arrangement is fixed, let's say they are sitting only in this order A, B and C, where A is to the left of B and B is to the left of C. So we do not need to multiply this arrangement with any answer. So the number of ways in which n people can be arranged in n places such that x of them are always together and their internal arrangement is fixed will be given by this formula. If the internal arrangement is not fixed, then we need to multiply this formula n minus x plus 1 factorial by x factorial. Because their internal arrangement will not be fixed, we'll have different options. Like in this case, for three people, we'll have 6 options. Let us now consider another case in which there are three people A, B and C such that A is always to the left of B and B is always to the left of C. So there are n people out of which these threes are arranged in this fashion. So this can be done in n people can be arranged in n places in n factorial ways. Now as I have shown previously, for these three people there can be 6 different arrangement, but we do not have to consider all the 6 arrangement. We only need to consider the arrangement in which A is to the left of B and B is to the left of C. So as you can see here, there is only one arrangement which will satisfy this condition. So what we will do is we will divide this n factorial by x factorial, since we need to consider only one case. So as many number of peoples are there, we will have to divide it by x factorial. So the number of ways in which n people can be arranged in n places such that a fixed arrangement pattern for x of those people is given. It can be done in n factorial by x factorial ways. Let us now understand the concept of conditional distribution of things. In the first case, we need to distribute n similar items to r people such that each of them gets any number of things. So there are n items in a group, they are all similar, and we need to distribute items from this group to our people. And these people can get any number of things. They can get 0 thing, 1 thing, 2 thing, or all n things. So how it is to be done? Let us take this example first and understand the working behind this. Mohan wants to distribute 5 similar balls to 3 kids such that each of them gets any number of balls. So there are 5 balls which are of same type and he needs to distribute it to 3 kids. So this distribution of 5 balls to 3 kids such that each of them gets any number of balls can be done in such a way that the first boy gets all the 5 balls, the second boy gets 0 ball, and the third boy also gets 0 ball. Or this 5 can be broken down into 4, 1 and 0. In this case, the first boy is getting 4, second boy is getting 1, and the third boy is getting 0 balls. We can interchange these positions also. The first boy can get 1 ball, second boy can get 4 ball, and third boy can get 0 ball. This internal arrangement can be done in 3 factorial ways. Since there are 3 things that need to be arranged in 3 places, it can be done in 3 factorial ways. Whereas in the first case, the 5 balls can go to any of these 3 kids, so it can be done in 3 ways. So this 3 factorial is 6 and this is 3. Again, this division of 5 balls can be done in 3 to 0, which internally this can be arranged as 3 factorial ways, which is 6. This distribution of 5 balls can also be done in the way 3, 1, 1. Their internal arrangement can be done in 3 ways, so this will give us 3 more. Further, this distribution of 5 balls can be done in 2, 2, 1, and their internal division can be done in 3 more ways, which will give us 3. So the total number of ways in which these 5 balls can be distributed to 3 kids will be 3 plus 6, 9, plus 6, 15, 15 plus 6, 21 ways. So this is how you can distribute 5 balls to 3 kids such that each of them gets any number of balls. By using the formula, it can be done in n plus r minus 1 c r minus 1 ways. So there are 5 balls. It needs to be distributed to 3 kids, which is 5 plus 3 minus 1 c r minus 1. There are 3 boys, so this will be 3 minus 1. So we'll get 7c2, which is nothing but 7 factorial upon 5 factorial into 2 factorial. We'll get 7 into 6 by 2, which will be 7 6 are 42 by 2, which will give us the answer as 21. So this distribution of 5 balls to 3 kids can be done in 21 ways such that each of them gets any number of balls. So by using this formula, you can find out. You don't have to list down all the possible combinations and then find in how many ways can these combinations be distributed internally. You can directly use this formula. Let us see now the second condition. Distributing n similar items to r people such that each of them gets at least one of the things. So in this case, n items are to be distributed to r people such that each of them should get at least one thing. In the previous case, it was possible that one of them or two of them can get zero number of things. But in this case, each of them should get at least one thing. So this can be found out by using the formula n minus 1 c r minus 1. So let's take this example. Mohan wants to distribute 5 similar balls to 3 kids such that each of them get at least one ball. So this will be 5 minus 1 c 3 minus 1. So it can be done in 4c two ways, which will be 4 factorial by 2 factorial into 2 factorial, which will be 4 into 3 by 2, which will be 6. So this distribution of 5 balls to 3 kids can be done in 6 ways such that each of them gets at least one ball. Let us consider the third case. Distributing n dissimilar things to r people such that each of them gets any number of things. Now we have a case in which the items to be distributed are dissimilar. In the previous two cases, the items which were to be distributed were similar. So this was also similar and this was also similar. Now in this case, the items to be distributed are dissimilar. And again, they need to be distributed to r people such that each of them gets any number of things. So let us say there are again 5 chocolates C1, C2, C3, C4 and C5, and I need to distribute these 5 chocolates to 3 people, P1, P2 and P3, such that each of these people can get any number of things. So for the first chocolate, I can give it to any of these 3 people, so I have 3 options. For the second chocolate, again I can give it to any of these people, so I'll have another 3 options. I can give it to P1, P2 or P3. Likewise for C3, C4 and C5 also, I'll have 3 options, 3 options and 3 options. So the total number of ways in which these 5 chocolates can be distributed to 3 people will be 3 into 3 into 3 into 3, which will be 3 raised to 5. So if there are r people, instead of 3, if there are r people, so this distribution can be done in r raised to n ways. So n things are to be distributed to r people. So for each of these n things, I'll have r options. So it can be done in r raised to n ways. Let us consider this example. In an exam which consists of 20 questions, each question can be answered in either yes or no, or it can be left unanswered by a student. In how many ways can the student attempt the paper? So there are total 20 questions, and each question can be either answered as yes or no, or it can be left unanswered. That means the student can choose not to answer that question. So for dealing with each of these questions, he has got 3 ways. He can either answer it as yes or no, or he can leave that question. So there are total 3 ways. So for the first question, he will have 3 ways. For the second question, 3 ways. Third question, again 3 ways. Like this way, for the 20th question, he will have 3 ways. So the total number of ways in which he can attempt the paper will be 3 into 3 into 3, 20 times, which will give us 3 raised to 20 ways. Let us move ahead. In this case, we are distributing n dissimilar things to r people such that each of them gets any number of things and the order of their internal arrangement is also important. Let us consider this example. At a railway station, there are three ticket counters. In how many ways can 10 people stand in a queue in front of these three counters? So there are three counters C1, C2 and C3 and there are 10 people. So all of these 10 people can decide to stand in front of counter 1. Now these 10 people are 10 different people, P3, P4 all the way up till 10. So who is standing at the front, who is standing at the back, or who is standing basically at which position, that is also important. So this is the meaning of this word. The internal arrangement also matters. So where on which counter they are standing is also important, and in which order they are standing at each of these counter is also important. So in how many ways can this arrangement be done? This can be done in n plus r minus 1 factorial upon r minus 1 factorial ways. It is not possible for us to manually list down all of these combinations. We can directly use this formula and arrive at our answer. So here we have the value of n as 10. We need to distribute 10 people to 3 counters. So we are distributing n dissimilar items to r people. So here your items refer to your people, which are 10. So n is equal to 10. And we are distributing it to r people. So your people here is your counters. We are basically distributing 10 people to 3 counters. So the value of r will be equal to 3. If we substitute these values here, we will get 10 plus 3 minus 1 factorial divided by 3 minus 1 factorial, which will be 10 plus 3 is 13 minus 1, 12 factorial. This whole thing will be divided by 2 factorial. So as you can see, this number, whatever it comes out to be, it will be a huge number, 12 factorial divided by 2. So manually it is not possible to list down all the combinations. You can directly use this formula to arrive at your answer. Let us now understand the concept of group formation. Suppose there are n people and these n people are need to be divided into two groups of p people and q people. So basically we are forming two groups, one group containing p number of people and another group containing q number of people. So how this can be done? So basically what we need to do is we need to make a selection of p people out of n and we also need to make a selection of q people out of n. So then they will be divided into two groups. But when we select p people out of n, so the number of people left in the group will be n minus p, which will be equal to q. So we do not need to select q people, they will automatically be selected. When we select p people, the people which will be left in the group will automatically become equal to q, hence they need not be selected, they are already selected by default. So the total number of ways in which n people can be divided into two groups basically means selection of p people out of n people, which can be done in ncp ways, where n is p plus q, c p ways. So this can be written as p plus q factorial, the whole divided by p plus q minus p factorial. I am using the formula for NCR. So this will become p plus q minus p factorial divided by r factorial, which in this case is p factorial. So this will become p plus q factorial, the whole upon p and p will cancel out, p factorial into q factorial. So if we needed to divide this n people into three groups of sizes p, q and r, so this can be done in p plus q plus r factorial ways, the whole divided by p factorial into q factorial into r factorial. Likewise, you can extend this same logic for any number of groups. Now let us consider this formation of two groups. So two groups can be formed in p plus q factorial, the whole divided by p factorial into q factorial. Now what if the sizes of both the groups are equal? So p is equal to q. So in this case there will be two conditions. In the first condition, both these groups will have distinct identities. That means both these groups will be distinct. So in this case, the total number of ways in which the group of n people can be divided into two groups P and Q such that sizes of both the groups are equal and both the groups have distinct identities will be equal to P plus P. We'll replace P as equal to Q in this equation. So this will become P plus P factorial divided by P factorial into P factorial, which can be written as 2 times P factorial the whole divided by P factorial the whole square. In the second case, if both these groups do not have distinct identities, that is both these groups are equal or similar in nature, there is no difference between these two groups. So all you need to do is divide this equation by 2 factorial. Since both these groups are similar in nature, there is no distinction between these two groups. So this will become 2 times P factorial the whole divided by P factorial the whole square into 2 factorial. Similarly, for three groups, we can arrive at our formula for distinct identities and similar groups. So in case of three groups, if n peoples are to be divided into three groups of sizes P, Q and R, such that size of each of the groups are equal, P is equal to Q is equal to R, this division can be done in 3 times P factorial the whole divided by P factorial the whole cube is. If the group have distinct identities. If the group does not have distinct identities, we'll have to divide this equation by 3 factorial. So in this way you can form groups of different sizes. Let us now understand the concept of circular permutation. In this we'll understand two important formulas, number of ways of arranging n items around a circle and number of ways of selecting k consecutive things out of n in a circular arrangement. Now in linear arrangement, we had one start point and we have one end point. We had some reference. But in case of circular arrangement, you will see, suppose if I want to place 4 people along a circle. So I do not have any start point nor I do have any fixed point. If I wanted to arrange 4 people in a linear arrangement, then in this case I can say I have a start point, I have an end point. But in case of circular arrangement, there is no such thing as a start point or an end point. So for that we'll have to first create a reference point. So out of these n people, I'll take one person and make him sit at any of these n places. So suppose I make that one person to sit at this place. So now this is my reference point. So my seating will start from this point. It will go all this way and come and end at this point. So now I have a reference point in this case. So now all I need to do is place the remaining n minus 1 people at these n minus 1 places. So for that, I'll use the concept of n people to be placed in n places can be done in n factorial ways. So n minus 1 people at n minus 1 places can be done in n minus 1 factorial ways. Now in case of people sitting around a circular table, there is some distinction between the clockwise and the counterclockwise arrangement. So if I have taken this as a reference point, the person sitting at this point will be at the right hand side of this person and the person sitting at this point will be at the left hand side of this person. So these two people are different people. Whereas in case of a necklace, the beads in the necklace are all the same. So if I take this as a reference point, then this bead and this bead, they both are basically the same bead. It is not like this in case of people. In people, the person sitting at the right hand side and at the left hand side will be two different people. But in case of a necklace, the beads to the left as well as to the right will be one and the same. So for in cases where there is no distinction between left hand side and the right hand side arrangement, the n items can be arranged around a circle in n minus 1 factorial, the whole divided by 2 factorial base. Because there is no distinction between left hand side and right hand side arrangement. Now let us see how to select k consecutive things out of n circular things. So again there will be two cases. where k is less than n. So let's say out of n people, 1, 2, 3, 4, 5, 6, 7, 8, I need to select 3 consecutive people. So 3 is definitely less than n. So this selection of 3 consecutive people can be done in n ways. Since it is a circular arrangement, you can start from this position, these 3, then you can select these 3 as well, then these 3 as well. In other words, each of these individual person can act as your starting point. So selection of k consecutive things out of n things in a circular arrangement such that k is less than n, it can be done in n ways. In the second case, when k is equal to n, so you can just think of it mentally, it can be done in only one ways. There is no other way. You have to select all the people and they have to be in a consecutive manner, so there will be only one way in which this can be done. Let us now understand our last concept in this video, which is the dearrangement concept. Now dearrangement basically means wrong arrangement. Let us understand what I mean by dearrangement with the help of this example. 8 letters are to be put in 8 addressed envelope such that only 5 of them goes into correct envelope. In how many ways can this be done? So out of 8 letters which are to be put into 8 envelope, only 5 of them should go into correct envelope. So that means the remaining 3 should go into the wrong envelope. So what we need to find basically is in how many ways can we put 3 letters in wrong envelope. So for that we'll have to use the concept of dearrangement. The formula for dearrangement, that is of wrong arrangement of n things, is given by n factorial into 1 upon 0 factorial minus 1 upon 1 factorial plus 1 upon 2 factorial minus 1 upon 3 factorial and so on. So we have alternating signs. We have a plus here, minus, plus, minus, plus, minus, and in the denominator we have 0 factorial, 1 factorial, 2 factorial, all the way up till n factorial. Now if you notice 1 upon 0 factorial, the value will come out to be equal to 1. 1 upon 1 factorial, the value will again come out to be equal to 1. So 1 minus 1 will become equal to 0. So this part of your formula, you can ignore it straight away. So your formula will start directly from n factorial into 1 upon 2 factorial minus 1 upon 3 factorial plus 1 upon 4 factorial minus 1 upon 5 factorial all the way up till minus 1 raised to n upon n factorial. Now dearrangement of one thing is not possible, because if there is one letter and it is to be put in one envelope, there is no way in which I can put that one letter in a wrong envelope. Likewise, if I want to find dearrangement of 3 things, we can straight away use the formula, which is 3 factorial into 1 by 2 factorial minus 1 by 3 factorial. So this will be 3 factorial, which is 6, 2 factorial is 1 by 2, and this will be 1 by 6. So from here we'll get 3 minus 1, which will be equal to 2. So dearrangement of 3 things will be equal to 2. So in this question what we need to find out is how many ways can in how many ways we can put 8 letters into 8 address envelopes such that 5 of them goes into correct envelope and 3 of them goes into wrong envelope. So for that we'll have to first select which are the 3 letters that needs to go into the wrong envelope. So out of these 8 letters, we need to select 3 letters which we will put in the wrong envelope. So for these 3 envelopes that we have selected, it can be done in 8C3 ways. We have to put in the wrong envelope. So we'll find out the dearrangement of 3. So dearrangement of 3, as we have found out, came out to be equal to 2. 8C3 will be 8 factorial upon 5 factorial into 3 factorial, which will come out to be 8 into 7 into 6, the whole divided by 6. So 6 and 6 will cancel out and this thing has to be multiplied with 2. 8 7s is 56. 56 into 2 will be 112. So this task of putting 8 letters into 8 address envelopes such that 5 of them goes into correct envelope and 3 of them goes into wrong envelope can be completed in 112 ways. So this is all about the concepts of permutation and combination. In the next video, we will solve some problems based on these concepts. Thank you.